Now, when it comes to spontaneity or determining whether redox reactions are spontaneous, we've often solely looked at the reduction potentials. And while that is not inaccurate, reduction potentials are part of what we would call the overall spontaneous nature of a reaction. It's not the complete picture. Ultimately, what determines if a reaction or a system is going to be spontaneous with its constituents is thermodynamics. What I mean by that is when we're deciding whether a reaction is going to be spontaneous, we're really supposed to look at all the available energies in all the forms in a system and not just the energy available in one way, namely the reduction potentials or the ability of the two substances involved to lose or gain their electrons. Now, it's not that there's anything inherently wrong with relying upon reduction potentials to determine whether the reaction is going to be spontaneous or to determine what reaction is going to happen at the anode and the cathode of an electrochemical cell. It's just when you can't account for all of the aspects of a situation, like the flow of energy here, you can get surprises or things that don't match your calculations when you're looking at it through a narrow scope. Now, in science, we call those surprises anomalies. And so we have a formula that works most of the time, but there are certain situations that demand us to have a holistic view of what's going on. And so that certain calculation that usually works, that all of a sudden doesn't work anymore, that is what we call an anomaly. And for today's video, one of the anomalies that we're going to talk about is the chloride anomaly that you usually see in the electrolysis of solutions that contain chloride ions. So let's want to determine the reactions at each site and the total cell voltage for the electrolysis of brine, which is your sodium chloride solution. So like we normally would, we would list all the ions that are present in this solution. Since it is a solution, we do have to list water. Next, we're going to identify all the oxidizing agents and reducing agents, and that would be using our reduction potential table or our redox table available in most chemistry books. Now, when we're looking at all the reducing agents here, if I look at water at a value of positive 1.23 volts, this would be water as a reducing agent. And I look at chlorine, and there's chlorine with water, but we want the strongest one possible. That's plus 1.36. Well, water is stronger than your chloride ions because remember that the closer you are to the bottom of the right-hand side, the stronger you are as a reducing agent. So water should be at the anode. And then if we look at the cathode, well, you have Na+, which is relatively weak. It's almost at the bottom of the scale here. And then water again. So it looks like here that your water is going to be at the cathode and the anode, and that's possible. Remember, the disproportionation is a type of redox reaction that can occur. So you could have the same substance at the anode and the cathode. So that would mean that we can expect the following at each site. The cathode reaction would be the reduction of water, which is H2 gas plus 2OH bitus. And then at the anode, you'd have the oxidation of water, which would yield to 4H plus, or the production of hydrogen ions or hydronium ions plus oxygen. And then, of course, expelling 4 electrons. Now, some of these things are very testable. So if we do this reaction, we can test for the presence of these to properly and verify what is actually going on at the cathode and anode. So this here is very verifiable. Hydroxide ions, they respond quite well to pH paper, to litmus paper, and as well as to indicators like phenolphthalein, right, which turns a nice pink color from clear. And so for pH, we're going to look for anything that is greater than 7. For litmus, we're going to expect it to turn blue. And then at this site as well, the H plus is quite testable, where it'll also respond to pH and it'll yield a pH less than 7. For litmus, it would turn litmus red. And then for indicators, you could use bromothymol blue. It'll turn a nice yellow color. So what we're going to do is we're going to actually put this, you could say, system to test. We're going to electrolyze brine solution, and we're going to verify and see if these are indeed what they produce. The other thing I should mention is that, remember, since this is an electrolytic cell, you're going to have to connect the cathode to the negative terminal of the battery and the anode to the positive terminal. And what does that mean? Well, your anode is going to be connected to the red terminal, and then your cathode is going to be connected to the black terminal. Let's set this up and see what we get. Starting to smell like bleach, or like a swimming pool. Wait, there's only one gas that smells like a swimming pool. With the threat of chlorine gas looming, I decided it was safe to shut off the power supply and stop this electrolysis reaction. And the result of this reaction with the bleach produced, the neutral pH, could only mean one thing, that at the anode, it was chloride ions that were oxidized into chlorine gas instead of water. So what happened here was that it turns out that it was chloride ions that got oxidized at the anode instead of water. And the reason for that is, while the reduction potential of, you could say, chloride ions are higher, which means that they're weaker reducing agents, they still occurred at the anode, although water is a stronger reducing agent. The reason why this is the case for this specific anomaly is that the activation energy of water, when we're converting from water to hydrogen gas and oxygen gas, is much higher than it is for chloride ions to convert and give us chlorine gas. And so when we consider the total energy, it's simpler or more energetically favorable for our anode to oxidize chloride ions to chlorine gas. Now, more specifically, it's the production of oxygen atoms from the oxidation of water that really increases the activation energy in this case and causes really the oxidation of chloride ions into chlorine gas instead. And so, because of how difficult it is to create oxygen atoms from water, you can always expect chloride ions to oxidize at the anode rather than water at the anode, even though water is a stronger reducing agent. So in short, the chloride anomaly is this, that when water and chlorine or chloride anions are competing at the anode, right, for their products, or for their reaction, I should say, chloride ions are always going to win because it's just simpler to make chlorine gas than it is to make oxygen gas. But it's only when water and chloride ions are competing for the anode. And so we're going to erase this half reaction and we're going to write what actually got oxidized at the anode, and that would be the chloride anions here. And so when we calculate our cell voltage, we would have to use the oxidation of chloride anions value instead of the water as the reducing agent. And so with the adjusted cell, we now have a cell voltage of about negative 2.19 volts, and that would be the minimum energy required. And just to answer, where did that bleach come from? Well, bleach is basically when you take chlorine gas and mix with hydroxide ions, that makes hypochlorite. And so because in the whole entire solution, we had hydroxide ions from the cathode and then chlorine gas from the anode, there was a slight mixing since they're in the same tube, and that created the bleach.